So, excellent. So the problem that I'm going to explain for us is textbook problem 1.40, which a lot of us got part 2 wrong. And so I'm going to explain what we did wrong and what the right answer is. So just to refresh, the problem is a cannon shoots a cannonball at an angle theta, and we're asked to come up with the position as a function of time and then find the condition for which the magnitude of the displacement vector is always increasing, and I'll get to that in a second. But this is just a really simple problem where the ball has 1 force in the y direction and 0 forces in the x direction. So when we apply Newton's second law and turn it into a differential equation and integrate twice, we come up with our familiar kinematic equations. So all that just to say, we have these equations, and now we're going to use them when we talk about the magnitude of the displacement vector. So we'll move a little bit over here to kind of drawing a picture of what we're looking for. And we're looking for a theta such that the magnitude of the displacement vector is always increasing. And you can kind of think of it as you've got, like, if it's at an angle less than the critical angle, it goes far, and obviously, like, the displacement vector is always increasing. But then you can think about if it's the theta is larger than the critical angle, it just sort of goes up and down. So the displacement vector is increasing, but then it reaches the top and then it's decreasing. So this is our expression for that magnitude. I'm going to call it r of t, and it's just square root of x squared plus y squared, where x and y are both functions of t that we found in part A. And for convenience sake, we're going to look at r squared as opposed to just r, just because of the pesky radical. It doesn't add anything to the problem, or loss of generality or anything like that. So what we're going to do is we're going to take the first derivative with respect to time, and it is a lot of algebra, so just take a moment and appreciate the algebra of taking the derivative of both x squared and y squared. So this is the derivative in all of its ugly chain rule glory, and then you simplify. I've even skipped a step in the simplification. And so you get it down to this beautiful little thing, and you set it equal to 0. And so then you've got a t squared, and a t cubed, which is only 1 power of t away from a quadratic equation, which we can then use our quadratic formula on. So I'm going to go ahead and just take away this t, divide by 1 power of t. We don't lose anything by doing that because it's equal to 0. So now we can just use the quadratic formula. This is t squared, quadratic formula on it, negative b plus or minus the square root of b squared minus 4ac all over 2a. And we get over here, and nothing quite yet, you know, what's our theta critical, blah, 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 nothing helpful. But then look, under the radical, there's this really weird thing, 9 sine squared theta minus 8. And we can see that if 9 sine squared theta is greater than 8, then t is going to be real. And that'll be great. Yay! But if 9 sine squared theta is less than 8, then our time is going to be imaginary. And that corresponds, you can think of that physically as the displacement vector is not always increasing. That's how I think of it. So then, so we want to find the condition where 9 sine squared theta equals 8. So we will come over here to this board. There we go. That's just in words. Sine squared theta is equal to 8 over 9. Just pull it over and divide. Sine of theta is equal to the square root of 8 over 9. Theta is equal to the inverse sine of blah, 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 71 degrees, which is not the angle that we got. We got, I think 45 degrees was our angle. And the problem that we solved originally, that most of us solved anyway, was the problem of maximizing distance. Like, what's the critical angle that you want to shoot the cannonball off at in order to get that maximum distance? So that was wrong. That was not the question we were asked. But this is the correct answer, and this is how you get it.